Hello everybody, I'm back again to talk more about equilibrium. I'm roughly on page 3 going into page 4 of the note sets. So today we're going to compare Q and K, understand the relationships, and then future videos we're going to spend a lot of time on how to actually calculate equilibrium constants for given reaction systems and looking at more of the mathematical details. I just want to focus right now on concepts. So let's just take the case, let's pretend A and B are in the aqueous phase, just for the sake of argument. In that case, we could write Q for a reaction, the reaction quotient. I'll just use a subscript C to be the molar concentration of B over A. I'm taking the simplest case where you just have two things. The coefficients are ones to make it really simple. And then we have Kc equal, it's the same thing, the same form to describe the system. This is the equilibrium constant, really the thing we're really interested in here. And so I'm just going to put an arbitrary little profile over here where there's a value of K, the equilibrium constant, not to be confused with the rate constant, and we have time. The time scaling is arbitrary. Well, that's a function of the kinetics of the system, how long it takes to come to equilibrium. Let's take some cases, and these are all summarized in page 4 of your unworked out note sets. Let's take, we have case 1, we'll call it that, where Q is less than K. Where Q is less than K, we say in that case the reaction heads right towards products. Why do we say that? Let's look at this here. Well, products are written on the right. The form of this is products over reactants. So if Q is less than K, means we have too little of B relative to A to give us the value of K. So we have to build up B relative to A. So that when we say the reaction head right, it means for that particular case, we'll get an enhancement of the forward rate relative to the reverse rate of this reaction. And so in the second case, so on the diagram, the way this will look is when Q is less than K, let's say Q starts out down here somewhere, what you'll see is that when it heads to the right towards products, it's going to increase the value of Q. So let's say here's Q. See, we'll put a little 1 here, meaning like case 1. It's going to increase this way towards K. This is the value for K. I just drew as the midline here on this axis. So on the other hand, case 2 obviously will be Q greater than K. And we say in that case, I'll make it like a big K, reaction heads left, which we define in chemistry as towards the reactants. We always write the reactants on the left, the products on the right, and it's the converse case. And so if we have Q greater than K, we have too much B relative to A for the system to be at equilibrium. So what do? We head left by increasing the rate. I'll make this super big. Going in reverse relative to the rate going forward. So we build up B relative to A. And so the way this will look diagrammatically for case, we'll call it case 2, is we'll put Q up here. And then it goes down like that till it achieves the value associated with K by changing composition by heading towards reactants. You'll get to a certain point where you have that correct ratio, and at that point the rates will equal each other. The rate forward and rate reverse, well, in that case I'll make these like equal, will be equal to each other. And then the third case is Q is equal to K, the equilibrium constant. And you can put subscript C on here. This is all applicable to QP and KP as well. And then you're at equilibrium. You're at equilibrium. That's where the system is ultimately heading. So those are some big concepts. I have this diagrammatically worked out a couple different ways on page 4 of the notes. I drew one of them here. You can take a look at the other ones. So there's a little exercise on page number 5 that I'll go through. It's a skill builder. It's conceptual. Rework it on your own to understand it. And there's similar problems in the note sets. In this problem, we're dealing with the reaction system H2 gas plus I2 gas in equilibrium with, let's see here, we have 2HI gas. And it's at a certain temperature. And what we do is we're preparing the system with certain initial concentrations. And so I'll just say here we have initial concentrations. So we have here 0.50, and we'll do this, we can do this in the gas phase, we can do it in partial pressures or molarity. I'll choose to do it in molarities. So we'll use the KCs, which is just a notational issue. We got 0.50 molar of the HI, and we've got, let's see here, we got 0 molar, I'll write it 0.00 just to be proper, molar of HI, right? So we start the system off with just the reactants, no products, and this is a known reaction that has a known equilibrium constant. So what we see is that at this certain temperature, which I don't state what it is, but it's just a certain temperature, is that, well, first let's write down what K and Q look like. Q is going to be equal to, we'll put QC to be proper, HI, molar concentration squared, over H2 and over I2, which numerically in this case is real simple. It's going to be 0. I'm not even going to write it squared. 0 squared is 0 over 0.50 squared, which is equal to 0, right? So we know Q is going to be less than K, right? Q is definitely less than K in this case. It would be similar to this. It's 0 in this particular case, which is actually pretty common. You prepare a system in that case with just the reactants and no product present. So that's actually experimentally very easy to do. And what we see for this is that at equilibrium, I'll write it here, at equilibrium, we observe over time, I'm not going to say how long it gets there, that's a kinetic question, we end up with, let's see here, we have 0.11, 0.11, 0.78. We give it time. We may know this from reading publications or a book, these values, but the thing is we give it enough time to ensure it becomes the equilibrium. We notice at a certain point there's there's a constant amount of this material. When we do measurements and there's a constant amount of this, the system is not changing. So we're at equilibrium. We have to give it enough time to ensure that's occurring. But then when we write K for this, it's equal to 0.78 squared. And then we have 0.11 squared, which according to my math gives me to 2 sig figs. I'll just write 50. So check the math out with that. Conversely, we could have another setup where we have another set of conditions where we have, let's see, we have 0 for the H2, 0 for the I2. This is another circumstance. Another experiment was prepared. We only start that system out with HI, and we end up with, let's see here, 0.50. We started out with that. So in that case, the way this looks is we have 0.50 squared in the second trial for Q when we set up the experiment. And when we have 0 down here, 0 times 0, 0. Now that's undefined mathematically, but you can think of it in the limit as it's approaching 0, that this is exploding up towards infinity. It's, this is practical math. This is undefined, but you can picture as you're approaching 0, this is, this becomes small and small and small. This is going to infinity. So that's the case which we can prepare in the lab as well. We can put some HI in there and let it establish equilibrium. And so in that case, what's observed, and we'll do the math for this later, is that equilibrium, we end up with something different. We end up with 0.0, we have to get this right here, 55 for the H2, 0.055 for the I2, and we end up with 0.39 for the HI in terms of its molarity, which gives us something a little different. We have HI squared, so we put in a 0.39 molar squared, and then we have, let's see here, we have the other two are 0.055, I should put a 0 out here, molar squared, because they're both 0.055 and there's two of them, and that ends up being to 2 sig figs 50. And so it ends up being the same value. The big point of it, the take-home point, is that, and this is all summarized in the table in your book, is that we start off with two different sets of initial conditions. I took the extreme. In one case, we have 0 of the HI. In the other case, we have 0 of the reactant species. But we converge over time to the same equilibrium constant, whether we started off above it, which we went as above it as we could. We have it at the theoretical limit of infinity for above it, Q, or below it, where we took it to the lowest value you could have. Never going to have a negative number here, but 0 would be the lowest. So I took it to the extreme to show that you converge, provided you can achieve equilibrium, you will achieve the same equilibrium constant as a function of temperature. As a function of temperature. So one of the questions I tend to ask is questions dealing with what changes the equilibrium constant. Does concentrations? No, the equilibrium constant is the equilibrium constant. That's a theoretical value of where the system wants to head to and the way we characterize it. And as a function of temperature. We will get into how temperature, and I actually go into more depth than the book does, on how temperature affects the equilibrium constant. We'll do that in detail with a treatment we'll get to in a lecture or two. So that's a big concept there. Let me erase the board. And well, actually, this is a good place to finish. I'm going to hold this video off right now. Well, next time what we'll do is some of the mathematical operations you can do with equilibrium constants, and we'll get into more of the mathematical aspects of the subject. So on that note, I think this is a good finishing point for this video. Maybe I'll make another one in a little bit. Have a good day, and I'm out. Take care.